Section 4.2. In the last section, we introduced the idea of the Laplace transform, we stated its definition, and we computed the Laplace transform for two preliminary functions. In an effort to gain familiarity with this operator, the Laplace transform, and in order to start building a catalog of known transforms of common functions, we're going to work through quite a few examples in this section. Here's the definition of the Laplace transform as a reminder, and let's go ahead and get started. In example 1, we're asked to find the Laplace transform of the function t. F of t equals t. I'll start by putting that function into my definition. Now, in order to evaluate this integral, I'll need to use integration by parts. Here I've identified the ingredients required for integration by parts and applied the algorithm appropriately. I want to go ahead and evaluate this second integral before I think about these bounds. So let me go ahead and evaluate that integral. Evaluating this second integral gives me this expression here. And now this overall expression needs to be evaluated at these bounds. When t equals 0, I can actually plug in t equals 0. But as we saw in the previous section, as t approaches infinity, to accommodate this quote-unquote bound, I need to introduce an appropriate limit. So evaluating at the bounds, I get this expression here. And if I look at these terms in the limit, I know for sure that as t grows without bound, so long as s is positive, then this term will go to 0. And if I look at this first term as t grows without bound, I actually have t times e to the negative st. Again, the convergence here is contingent on this s being positive. But as long as that's true, this exponential, which is heading to 0, will dominate over this t, which is growing without bound. Technically, I should be applying L'Hopital's rule, but I've done that enough that I know that in this context, this exponential will win the battle. And even though this t is growing infinitely large, this exponential will grow to 0 faster. Therefore, this term will also go to 0. Again, the convergence of those two terms is contingent on s being positive. So I'll note that down here as part of my solution. So if those two terms go to 0, then if I look at these terms here, I guess this term is 0 times something, so that'll go to 0. So then all I'm left with is this term here. There's a negative outside this parenthesis multiplied by that negative. So my final answer looks like it'll be 1 over s squared. The Laplace transform will be 1 over s squared. I'd like to try to start to identify some patterns here. So I'm trying to connect the fact that if I start with the function t, my transform is 1 over s squared. In an effort to extend that pattern, the next example has us calculate the transform of t squared. Let's see how that plays out. Let's start, as always, by putting the input function into the definition. I'm not surprised to see that I'll have to use integration by parts again. So let me go ahead and set up those ingredients. Now let me plug them into the structure of integration by parts. Now, in my previous problem, I went ahead and evaluated this integral fully before trying to deal with bounds, but there's actually kind of a little trick here. If I look at this integral, that integral seems sort of familiar. In fact, if I scroll up, that is exactly the integral that I started the previous problem with. That is to say, this integral, the integral from 0 to infinity of t, e to the negative st dt, is the Laplace transform of t. So I've already evaluated the Laplace transform of t. I know that it comes out to be 1 over s squared, so long as s is positive. So I can make that substitution, and instead of trying to actually work through the details of this integral, just directly plug in 1 over s squared. And I'll just reiterate that that substitution is based on example 1. This integral is exactly the integral I evaluated in example 1. Now, if I look at this first term up here, I'm starting to see a pattern. First of all, when I evaluate as t grows without bound, this exponential term will dominate any polynomial term. So as t grows without bound, the exponential will drive toward 0 faster than t squared will grow. Therefore, I know that this overall term will once again go to 0. And also, if I plug in t equals 0, I'll have 0 squared times, well, it doesn't matter, I'll have 0. So this entire front term, when I evaluate at the bounds, ends up just being 0. So my final answer will be that the Laplace transform is 2 over s cubed. Now, I've only worked through 2 examples, but I want to try to generalize. Down here in theorem 1, I've identified that the transform of t to the n will have some form for any non-negative integer, n equals 0, 1, 2. I have just recently done this Laplace transform calculation for n equals 1 and then n equals 2. So I'm going to try to generalize. Imagine what would happen if I was to evaluate the transform of t cubed. If I look back at example 2 and I imagine t cubed being here as my input, I would work through integration by parts. Notice that when I do that integration by parts, in this first step here, the t to a power term gets differentiated. And then when I've done the integration by parts, this integral will have t to 1 less power. In this particular example here, since I started with t squared, this integral is t to the first. If instead I had started with t cubed, this integral would be t squared. I would need to continue applying integration by parts. And notice that every time I apply integration by parts, I would differentiate this term one more time. In this case, we went as far as getting t in the integrand. If I had started with t cubed, then this integral would have been t squared e to the negative st, which is of course the transform of t squared. So I would have had 3 over s times this expression here. So one thing that's clear is that the power on the s in the denominator is going to increase as the power of t increases. In fact, looking at these 2 examples, it looks like the power on s is 1 larger than the power on t. So I could write that the transform of t to the n will have a denominator of s to the n plus 1. How about the numerator? It's not totally obvious, but I'd encourage you to just think about it for a little bit. Because I'm differentiating, and every time I differentiate, I bring the power down that was on the exponent, this numerator will be a bigger and bigger product, where each factor in the product increases by 1 for every higher power on n. Basically, this will give me a numerator of n factorial. Like I said, that's not totally obvious, but I would encourage you to stop and think about that for a sec. Verify that that's true. Based on that theorem, I could quickly evaluate, for example, the transform of t cubed. I know that will be 3 factorial over s to the 4th. 3 factorial is, of course, 3 times 2 times 1. So that'll be 6 over s to the 4th. And for any positive integer, non-negative integer power, I can quickly evaluate the transform of t to that power using this formula here. Let's take a look at the next example. In this next example, we'll find the Laplace transform of sine. I've actually introduced a sort of a generic coefficient on the t there. So I'm not just thinking of sine of t, but also sine of 2t or sine of 6t or sine of pi t. I'm trying to kind of deal with all of those at the same time. Based on the last 2 integrals, you may be able to predict what type of integral we're going to run into in this case. But anyways, let's go ahead and plug it into our definition. So you'll notice, of course, that what changes is this first part. The e to the negative st remains the same every time I go to evaluate a Laplace transform. So now this particular integral is one of the famous, what I call a feedback loop when doing integration by parts, where if I apply integration by parts multiple times, it just ends up circling back onto itself. I trust that you have encountered this type of integral previously, and so instead of working through all the details here, I'm going to go ahead and use sort of a formula. I've taken this formula from a reference from an old calc book, and I've written it up here in the corner. It's probably hard to see in the video, so you might want to take a look at it in the completed notes. But I can apply that formula here. It's in terms of e to the alpha t sine of beta t. So my alpha will be negative s, and my beta will be a. So, utilizing that formula, my integral becomes this expression here. So I have e to the negative st. Again, negative s is acting like the alpha in this formula. A is acting like the beta in this formula. So plugging in using the formula, I get this expression here. As I've seen in the last couple of examples, when I go to incorporate this infinite bound, this t growing without bound, the exponential will overpower any other terms. In this case, the other terms are sine and cosine, which will simply oscillate as t grows without bound. And so clearly, as t grows without bound, this entire expression is going to be dominated by this exponential term. And as long as s is positive, this exponential term will drive towards 0. So I believe that as t grows without bound, this entire expression will go to 0. And then I'll have some other quantity here that I'll get by plugging in t equals 0. So let's think about this a term at a time. This will be e to the 0, which will just be 1. So I'll have 1 over s squared plus a squared. And then in the parentheses here, this is s times sine of, so this will become sine of 0, which is of course 0. And then I'll have negative a cosine of 0, and cosine of 0 is 1. So this will become 0 minus a. Guess I didn't need that much room in my parentheses. So simplifying, this a will just become a coefficient here, and then this negative and that negative. So my final answer will be, so long as s is positive, I'll get a Laplace transform of a over s squared plus a squared. So if I start with sine of some number times t, the Laplace transform will be that number, that coefficient on t, over s squared plus that number squared. So for example, if I had sine of 3t, then the transform would be 3 over s squared plus 9. Let's keep rolling. Let's take a look at the next example. This next example is a little different because I have an unspecified function, f of t. So I don't know if f of t is sine or cosine or e to the 2t or t. I don't know what f of t is. But even without knowing f of t, I'm asked to compute the transform of its derivative, f prime. As always, I'll start by plugging this input function into the definition for the Laplace transform. And now, in a certain sense, it'll be impossible to evaluate this integral completely because I don't know what f is. So I don't know what its derivative is. So I don't have enough information to evaluate this integral in terms of getting a specific outcome. Nevertheless, I could apply the method of integration by parts, and I'll choose this unknown f prime. Well, I guess if this is the derivative f prime, then I should choose this to be my dv. Here's what I mean. When I set up integration by parts, these two components, u and dv, have to comprise my entire integral. And in this case, f prime is a derivative, so I'm going to choose it as my dv. Then anti-differentiating, v will just be the unknown function f. This will require me to choose e to the negative st as my u, which will yield negative s e to the negative st dt as my du. Now I'll implement the structure of integration by parts. Now there's kind of a lot going on in this expression. Let me actually start by looking over here at this integral. It may feel like we can't make any progress because I don't know what f is, and so I once again can't definitively evaluate this integral. But if you look at the structure, this is the integral from 0 to infinity of f of t e to the negative st dt. This is exactly the Laplace transform of f. So what I will do in my solution here is I'll actually write that as, this is going to be s times the Laplace transform of f, which I will write as capital F of s. So once again, I don't know exactly what f of t is, but whatever it is, to find the transform of the derivative, this transform will be defined in terms of the transform of the original function. Now, how about this first term here? The easy part is plugging in t equals 0. Let me do that first. If I plug in t equals 0, I'll have f of 0, and then I'll have e to the 0, so that's just 1, so I'll just leave it off, and I'll just write f of 0. So now, in order to evaluate as t grows without bound, I'll once again want to introduce a limit. And in previous steps, we've always been able to say decisively that this limit will go to 0 because this exponential term will dominate over f of t. In this particular example, it's not quite as clear-cut because we have no idea what f of t is. So what I'm essentially going to do is I'm going to make the restriction that this limit goes to 0. What I'm doing is I'm effectively requiring that this f of t be the type of function that it will lose this battle. As t grows without bound, I want this exponential to win. And there's actually a name for this. A function which effectively is beaten out by an exponential as t grows without bound is referred to as being of exponential order. So in a certain sense, this is limiting the functions that I can consider here, but the reality is that most functions, certainly all polynomials, all trig functions, and even exponentials for certain values of s will lose out to this exponential. So this restriction does enable us to still deal with a wide range of functions that are applicable in the context of differential equations. So since that term is now being forced to go to 0, this is effectively my final answer. So the transform of the derivative of an unknown function will equal s times the transform of the original function minus the original function evaluated at 0. This is a little strange, but you'll see that we utilize this property later when we're taking the Laplace transform of an entire differential equation. And actually, in the context of a differential equation, this f of 0 functions essentially as one of my initial conditions. So that will be a constant that's provided in the problem that I can plug in whenever appropriate. Okay, let's go ahead and take a look at example 5. In example 5, we're asked to compute the Laplace transform of f double prime of t. I already have a feeling that this will build off of example 4 somehow, but let's go ahead and work through the details and see how this plays out. I think at this point, having plugged f double prime of t into the definition, I think that in order to evaluate this integral, I'll once again use integration by parts. And in the same way that in the last example, I chose this derivative to be my dv, I think I'll do that again. Let's see. Here are the ingredients that I'll use for that integration by parts. And here are the quantities that I get when I enact the integration by parts algorithm. Once again, let me focus on this integral first. As we've seen in the last few examples, this integral is itself a Laplace transform. Namely, if I look at this integral, the integral from 0 to infinity of f prime e to the negative st dt, this is exactly the transform of f prime. Let me actually write that out. So here I've actually made that identification that this integral is in fact the Laplace transform of f prime of t. You know, in a sec when I'm done with this first term, I'll actually scroll back up and figure out what this quantity is and make the appropriate substitution. But first let's take a look at this first quantity. I will once again assume that as t grows without bound, this expression will go to 0. That is, I will be assuming that f prime is of exponential order so that as t grows without bound, this product will be driven to 0 by this exponential. And then I'll plug in t equals 0. So that'll give me f prime of 0, e to the 0. So I'll simply have f prime of 0. As I mentioned, I'll go back and scroll back up to see what this f transform of f prime is. Here it is. It's s times capital F of s minus f of 0. So making that substitution, I get this quantity here. And this is my Laplace transform. That is, this is the transform of f double prime of t. I'll go ahead and rearrange terms a little bit. I kind of like to put them in order of this s, so I will rewrite it like this. So I have the Laplace transform of f double prime equals s squared capital F of s minus s times f of 0 minus f prime of 0. Once again, these f of 0 and f prime of 0 terms will turn out to be initial conditions in the context of a differential equation. And so I can kind of think of this transform of the second derivative as s squared times the transform of the original function. This is a pattern from these last two examples that we could continue, and we could pretty easily identify the transform of f triple prime and then f quadruple prime as necessary. For our purposes in this lecture, we'll stop here with double prime, but you may see those results in the future.